Well, good morning and welcome back to AIEC Webinar Weeks. We're glad to have you. Hopefully we're bringing you not just products, but solutions. That's the whole idea here. So we're going to kick things off. This is our 42nd episode. So if you're just now joining us, welcome. If you're a returning attendee, welcome back. We're glad you're supporting us in this and supporting our associate members and our vendors. I know they appreciate the exposure, and we appreciate learning what they have to offer and those solutions that they can provide. So our presentation today will be about 45 minutes. We'll leave 10 or 15 minutes at the end for Q&A. As usual, please remain muted for the duration of the meeting. And if you have any questions, we definitely welcome those, and we would just ask that you submit those to the chat function, direct those to AIEC, and Brian and myself will moderate those questions to our presenter today. Another quick reminder, at the end of this series 3, which will end on the 30th, Ashley Graham will be sending out a survey. If you've attended any one of our webinars and you fill out that survey and complete it and submit it back, that will enter you into our grand prize drawing for a $100 Amazon gift card. So if that's something you might be interested in, we'd love to hear your feedback on our Webinar Week series and what your thoughts are, and just any feedback you can provide to us, we would greatly appreciate that. Ryan, who do we have this morning?
This morning we have Patrick Corley. He is an application engineer for the Hubbell Power Systems Arrestor business unit based out of the Aiken, South Carolina plant, where Hubbell manufactures arrestors, insulators, and cable accessories. He has been with Hubbell for a little over a year now, and prior to that, graduated from Clemson University with his bachelor's degree in mechanical engineering. So with that, I'll hand it over to you, Patrick.
Cool. Well, thank you guys for having me. We'll go ahead and get started. So we're going to talk a little bit today about distribution, arrestor application, and selection. Kind of go through a broad range of topics over the next 40-45 minutes. So like Brian said, I'm arrestor business unit application engineer. I've been with Hubbell for about a year, so I will be the point of contact for your Northeast, North Central, and Canada regions. So I'm probably you're going to be talking to if you reach out to the business unit for anything, for arrestors anyway. So get things started with a quick outline of what we're going to be talking about today. We'll start with some fundamentals, so kind of what an arrestor is and how it works and its function. We'll spend a little bit of time going over arrestor construction and kind of how we've done things for a long time as far as polymer housing and all of our distribution components. Then we'll go into application selection. So that's pretty much the process that we walk through when we get a request from a customer or place a bid or anything like that. And we'll end up today with installation coordination, and that's kind of a topic that honestly I could talk all day on. So we'll kind of hit the high points and kind of really, if there's any questions during that time, that'll be a really good time to discuss those. And then we'll have some questions, time for questions at the end. And I told Dan and Brian if anyone has a question that's kind of topic specific, they can definitely just kind of jump in and we'll talk about it at the time. So let's get started. So with some fundamentals, we'll talk briefly about pretty much an arrestor's job and what it does protecting electrical equipment from over voltages. So the cool thing is arrestors are very similar to this device that your laptop is probably plugged into right now, which is a surge protector. So if you see here these red MOV discs, which we'll go over that a little more in a minute, but these MOV discs are connected in parallel with the outlets. So if there's any kind of surge event or voltage spike coming into your house from a lightning strike or whatever, these MOV discs will take that voltage and pull it away and shunt it to ground to keep your laptop or computer or TV from getting fried. So it's kind of cool that something so small that everybody has in their house is the same technology that we use on our high voltage surge arrestors. So the high level purpose of a surge arrestor is essentially to respond to a high voltage spike. So the arrestor sits at line to line voltage or line to ground voltage at really high resistance. So when a lightning strike happens or a switching surge or any kind of impulse comes, it turns into a low resistance path to ground. And so it conducts the surge to ground and limits the voltage across the equipment, whether that's a transformer or a cutout or anything really. And then it has to reseal the follow current of 60 hertz current so it can operate again, for the next lightning strike or however, any switching surge, any kind of impulse, it is ready to operate again. So what do arresters protect? For the sake of this presentation, we're going to be talking mainly about, pole top transformers, fuse cutouts, and then, we can go into substation transformers as well, and even our protect-a-light or a line surge arrestor, which protects insulators, which is kind of more of a system reliability standpoint, a higher quality power with less interruptions. So before we get too deep, we'll go over a few key terms. I know I've already mentioned a couple of them, but the first one you'll see a lot is MCOV, which is a maximum continuous operating voltage. And so that is the continuous line to ground rating of the arrestor. So that's what the arrestor is going to sit at on your line. So like a 13/8 line, that's line to line. So we'll calculate the line to ground, which would be our MCOV. MOV is metal oxide varistor. So that's the name for the ceramic disc that we use in the arrestor. So that, similar to the little red disc in the surge protector, these are kind of where the magic happens in arrestors in general. Next is TOV, which is a temporary overvoltage. So this can kind of get a little confusing at some points. But first, it's a voltage greater than that at which a device or circuit is designed to operate. And it's at a 60 hertz frequency. So a TOV is not to be confused with an impulse or a surge of any kind. This is something that's lasting for, a tenth of a second or a couple seconds, where an impulse would be, in the microseconds. So this is a system generated overvoltage, not to be confused with an impulse. And then residual voltage, and this is pretty synonymous to many things, but this is the voltage level that the arrestor clamps to during a surge in kV. So it can be referred to as IR, protective level, clamping voltage, and discharge voltage. You'll hear me say all of those throughout the presentation. Oops. So what do arrestors protect equipment from? The first thing that probably comes to mind is lightning. A lightning arrestor is a common name. So they also protect against switching over voltages. And this is generally for more of a station geared topic, but line energizations, reclosings, fault occurrence and clearings, as well as like switching a series capacitors are all things that a arrestor will take care of and keep out of the system. So kind of start things off with a traveling wave theory. So this is kind of what happens when lightning strikes our line, whether it's distribution line or it doesn't matter, transmission line doesn't matter. So a median lightning strike is 31 kA. That's just kind of been studied over the years from our ground flash density studies and all things like that. Most strokes hit midspan, and the current will divide and then go in each direction. So we can use Ohm's law, V equals IR, to find out the voltage that your equipment or insulator will see in the event of a lightning strike. So for the sake of simple math, let's say we have a 20 kA stroke. So that'll divide in each direction. You have 10,000 amps going in each direction. And a normal surge impedance is 400 ohms. And you can calculate our voltage spike with this information. So 10,000 amps times 400 ohms is 4 million volts. So that's a lot. And any equipment, insulator, transformer, whatever on this line that has a basic insulation level, BIL, of less than 4,000 kV is going to flash over and be damaged. So it's pretty much always going to be destroyed. So when we have a surge arrestor in place, that outcome is going to be much different. So let's say that same 10 kA stroke travels down the line, and the arrestor has a given discharge voltage for a 10 kA stroke. So in this case, for an 8.4 kV MCOV surge arrestor, that the arrestor will discharge 31.6 kV. So as long as this insulator or transformer has a BIL of over 31.6 kV, you're never going to know anything happened. It's going to be fine. The transformer is going to be protected, and you're never going to know any lightning stroke, any hit anywhere. So that's the importance of a surge arrestor. So concept, like I said earlier, it's a high resistance at line to ground voltage. So it just sits there day in and day out, doing the same thing, pretty much nothing. So at the line to ground voltage, the arrestor conducts very little 60 hertz current, like in the milliamps, very, very small amounts. When a surge comes, it causes a traveling wave like we just talked about, with a voltage high enough to damage insulation. The arrestor turns on to become a low resistance path to ground during the surge event, and the surge is diverted to ground. And the arrestor conducts the surge for the duration of the surge, and it returns to being high resistance after the surge. Like I said, this happens generally in milliseconds or even microseconds, and the system operates as normal. So the arrestor is a reusable voltage switch. These are definitely not a one and done device. Can everyone still hear me all right?
Yes, we can. Thank you.
Cool. So here's what that change in resistance looks like. This is, again, something we can spend a lot of time talking on, but we'll just kind of hit the high points. So for the same 8.4 kV PDV100, which is our heavy duty distribution arrestor, at 8.4 here, it says, we're, 0.00005 amps. So, almost nothing, that's what it conducts, all the time, day in, day out. And so this is where the arrestor will last, forever. And the higher you go up this curve, the more current it conducts, of course, and the more heat it generates. So your TOV region will be somewhere right in here, and you're in the knee of the curve here. And so, you're conducting, a tenth of an amp, or a hundredth of an amp, a little, enough to generate heat. And heat is never good. So TOV is a very, very common failure mode for arrestors. So TOV generates heat, and the arrestor eventually gets into thermal runaway. And so the hotter it gets, the more current it conducts, which it eventually just can't cool itself off anymore, and then it runs away. And so on the other end of the spectrum, we have our impulse. So that's a switching surge or a lightning impulse. And so we're at 10,000 amps right here. And so our discharge voltage, like we said earlier, is about 31.6 kV. So the reason we can conduct all this current here is because it's such a short amount of time, in the microsecond range, super, super short. This region is not temperature sensitive. It really doesn't matter, like I said, because it's so short. And then our impulses can go on up from there, up even higher. So any questions on fundamentals before we move on to construction?
We don't have any questions yet, Patrick.
Okay, cool. We'll move on. So we talked about MOVs. This is kind of the heart of a surge arrestor. It's super complicated how all this, it's way over my head. You're asking the wrong person about MOVs, but so they're super fascinating though. So they're like a combination of zinc and other metals that are kind of fired in a furnace that we make in Wadsworth, Ohio. So all of our MOV blocks are made right up the road from you guys, probably, in Ohio. So a little bit about these. So they vary in height and diameter, of course, as you can see here. So the diameter, or the surface area, is a function of, well, I guess energy handling capability is a function of diameter or surface area. So our smaller diameter MOV blocks here are, more geared for distribution. And our big blocks up here, around 75 millimeters, those are for our station class or varistor applications. And the height is a function of system voltage. So, you stack these things on top of each other, of course, the same diameter, to get a different voltage. So you can kind of look at an arrestor and tell, well, that one looks like a 22 kV rather than like a 5 kV, just because of the height of it, clearly. So here's a cutaway of one of our distribution arrestors. Pretty straightforward. So our modules and housings are inserted, so rather than direct molded, which we think gives us an advantage because of have a lot more sealing interfaces here. We have grease on this module as well, but this is gapless module assembly technology. So our MOVs are stacked with a Belleville washer in the middle, and they are compressed between two aluminum terminals. And I want to say around 750 foot-pounds or so. It kind of depends. And then they're wrapped with a fiberglass epoxy, and then put in an oven and cured. So they expand a hair, but they're super durable. And then they are inserted in a polymer housing with two end plates on each end, and then a insulating disconnector bracket that we'll go over a little bit in a minute. So here's a little more detailed cutaway. So the green here is our MOV blocks. So in the picture before, you can see that the MOV blocks are white. So they're actually covered in like a glass coating, which kind of helps with moisture ingress and a little bit of a durability, for the assembly process. And then you can see our aluminum terminals here and our wrap pattern here. So now it's kind of a really proud product that we have here is our insulating bracket. So we pride ourselves with our capacitive graded disconnect here rather than a resistive graded, because it gives us several advantages. One of those is TOV handling capability, as well as more sensitive disconnection. So that kind of increases your reliability of your system, because I'll go over it more in a minute, but this disconnector will operate down to 1 amp, where the standard only requires 20 amps to disconnect it and take the arrestor out of system. So here we're going to talk about application selection real quick. This is kind of a topic that doesn't take too long, but it's pretty interesting nonetheless. So the topics that we think about when we have a request are, first is technology, then we'll think about installation location and lighting activity. So, if you're in the panhandle of Florida or anywhere in the Southeast, you're going to more than likely see a lot more lightning activity than you will somewhere out, in the Pacific Northwest. So that's something that we always consider. And like I said, TOV requirements. TOV is a failure mode that's pretty common and tough on arresters. So we definitely want to know as much about your system as you can provide. So generally that would be like a TOV magnitude and a duration in per unit of MCOV, or however you want to phrase it. But really important for us to know that. And then, like I said, our reliable ground lead disconnector is a big part of our reliability here. And then a strong housing material. These inserted ESP housings have been around forever. And we have, I want to say we just celebrated, I think in January, our 40 millionth polymer house distribution arrestor. So we have quite a few of them and quite a track record here with this product. So like I said, we're super proud of it. So the first thing we want to know if you ask us to provide you an arrestor part number is MCOV. So that's calculated using your system voltage and grounding considerations. So we'll need to know the MCOV. So you need to know your system voltage, and we'll need to know the type. If you have in mind like you want to use a heavy duty or a normal duty distribution arrestor, that's our PDV 65 is our normal duty, and our PDV 100 is our heavy duty, or a riser pole application. And we'll go over that more in a few minutes. It's kind of a deeper topic. And then we will need to know hardware. So in this case, we have a cross arm mounted arrestor on just a cross arm bracket. So we have endless possibilities that we've already created. So we more than likely can find what you're looking for, but even if we can't for some reason, or there's some specific orientation that you need, we can definitely create it with our design engineers or right down the hall. So super easy to get in touch with them and make exactly what you want. So here's a quick example of how we calculate MCOV. It kind of depends on the grounding consideration, like I said, and we have a little snippet from our catalog that kind of helps explain it. But so for a solid grounded system, that's your minimum MCOV. That makes it super easy. We kind of know how to calculate that. Our ungrounded or resistance grounded, it kind of depends on the application, but generally we'll upsize the MCOV to handle any kind of TOV requirements. And then a delta, which we don't see those a ton, but we'll pretty much always bump the MCOV up to where it can handle phase-to-phase voltage, just in case that neutral shifts during a fault. So here's a quick calculation. So we have a 13.2 system, line-to-line voltage. Our voltage regulation is 5%, and we can kind of accommodate whatever. We just need to know, up to 10, 15%, whatever. And we have a solidly grounded system for this example. So we have our 13.2 times our 5% voltage regulation divided by the square root of 3, which comes from your grounded system, and that gives us 8.01 kV. So that is the minimum MCOV that is required for your system. So you will go to our catalog and find 8.4 kV in this column here, solidly grounded, neutral. Find 8.4 kV, or anything above 8.0, excuse me. So in this case, it'll be 8.4. And so kind of a little trick here is this chart kind of helps select. So you have your nominal voltage and the solid grounded. So it's going to be at 8.4. Let's see. Here we go. Okay. So this is our TOV capability curve. This is another thing that we really see here. Okay, there we go. That we really spend a lot of time working on and honestly looking at. So that same 13.8 system or 13.2 system, 13.8 maximum. So that's with your voltage regulation. So if you have a 1.5 per unit TOV for 10 seconds, we can find that on this chart here, and anything to the left or below the line here. So that'll mean you're in the clear. The arrestor is designed to handle it. Arrestors are designed to withstand a given amount of TOV, but we need to make sure it's within those means. So here, 1.5 per unit, followed over here to 10 seconds. So we're right on this line, and we know that this arrestor will be able to handle that TOV and should not cause any problems. And so you see how the line plateaus here for all of these voltages. That's from our capacitive graded disconnect. So, up to a certain point, the capacitor can handle a given TOV indefinitely. So that's a huge benefit, because without the capacitive graded disconnect, this line will just go on down, and finally asymptote around the x-axis. So the capacitive graded disconnect is a huge benefit. So kind of a higher level, the products that we offer. So luckily for us, our polymer housed distribution arrestors are dual qualified. So that means the same one, it's the same arrestor for IEC International or IEEE, which doesn't really apply here, but we are dual qualified. So the IEEE standard has 3 duty types, light duty, normal duty, and heavy duty. Light duty, we do not have a product offering. I honestly don't know of anyone that does. It's just kind of a niche product line that is just not really worth having. But our normal duty here would be a PDV 65, like I said, and then our heavy duty can be broken out into 2 types. Our PDV 100, which is just a heavy duty, and then our PVR, which is a riser pole application. So the weird thing is they're both tested to the same amount, but the riser pole is sort of specialized, and we'll go over that in a few minutes. And then we have our under oil arrestors, which those are mainly sold to just OEMs for transformers. So they're under oil in the transformer can. So I honestly don't know a ton about them, but we do sell those as well. I believe those are the PV 65 blocks. So very similar discharge voltages in that case. So a little more about MOV blocks. our different types will have different size MOVs. And like I said, the larger surface area or larger diameter, you can handle more energy due to the more parallel current paths. So it's kind of like a water hose, so more paths in parallel lowers resistance, and it'll spread the surge current over a larger cross-sectional area. So that in turn will lower your discharge voltage and your current density. And like I said, greater energy handling capability. So this is kind of a good lineup for all of our arresters, ranging from about 29 millimeters to 75 millimeters. So this is a discharge voltage comparison for our different distribution product lines. So on this axis here, we have our discharge voltage for the same voltage system, 15.3 kV MCOV. This is our normal duty, heavy duty, and riser pole. So you can see that how the larger the diameter of block, as you can see here, the lower the discharge voltage. So if you have some sort of specialty equipment that has a lower BIL than normal, it would be recommended to upsize from a PDV 65 to a PDV 100, or even from a PDV 100 to a PVR. And this kind of carries the same trend in our station class. Just a little tidbit here. So we have a couple different products that use a 56 millimeter block up to a 75. So the larger the block, the lower the discharge voltage. So now we'll go on to hardware configurations. So on the left here, this is our base, most common sold part number. It's just the arrestor, no cap, no lead wires on an insulating bracket. So pretty simple, straightforward. Next, we have a little more specialized to a cross arm bracket and a wildlife cap. And then on the right, the far right, we have a wildlife cap with a lead wire going to the line side, and then a transformer ground strap with a transformer mounting bracket. So like I said, if there's any kind of specialty situations that you run across, feel free to reach out to us. We do this every day. We can definitely help you out. We have design engineers that are sitting right up the hall from us, so we can pretty much come up with anything you need. And we'll go into a little bit more detail here about our ground lead disconnector. So in the box here, you have just the insulating bracket. You have your arrestor out here and your ground connection here. So what happens is, the grading component conducts just, those milliamps of current, all day, every day. And then when the arrestor reaches end of life, that current, gets higher and higher, and it'll eventually spark over this gap and hit. This is a blank 22 cartridge. So it's a rimfire cartridge. So when that spark hits the rim of this cartridge, it'll, of course, increase the pressure in the bracket rapidly, and will separate this ground connection from the arrestor. So the arrestor will be taken out of system. Your breaker will operate briefly, so your lights will flicker one time, and then your system will be re-energized. So that's why it's important to have a reliable ground disconnector, because so your whole line doesn't get locked out because of an arrestor failing. So kind of here's a typical sequence of events. As you can see in the picture here, this is a disconnected arrestor. So you have a nice visual indication of a failed arrestor. You know what happened. The line lead, the ground lead is hanging down, is not anywhere close to the arrestor. So this arrestor is sitting at line-to-line voltage. So a couple things before I jump into the slide. So like I said, when it disconnects, this arrestor is sitting at line-to-line voltage. And with this bracket, it's designed to sit there for, a certain amount of time. But if there's any kind of contaminants, in the environment, such as like a salty area or any kind of like high pesticide that gets on this insulating bracket, it is possible for it to track because it's sitting at 13 kV. It's not designed to sit there indefinitely. We do offer a high track resistant bracket that is designed to sit at line voltage forever, but it's important to kind of keep up with checking your arrestors, because bad things can happen well, your line will get logged out essentially when the arrestor tracks across this bracket and shorts. It's not a super common, it's not a common thing at all, but it's definitely something to think about. So it's important to go and check, make sure you remove all disconnected arresters from service. So kind of got off track there, but so a typical sequence of events, for whatever reason, the arrestor short circuits. The disconnector, so it conducts too much current for too long of a time, and the disconnector operates, and you get this. The ground link falls away. The overcurrent protection operates, whether that's a fuse cutout or a recloser, and the system will re-energize, and the voltage will hold, and then the service is restored to the end user. So, like I said, your lights will flicker once, but it's not going to lock everything out. So the ground lead separates, you have a visual indication of separation, and that increases your system reliability. So here is the ground lead disconnector curve that I was talking about. So the IEEE standard requires that it operates at a minimum of 20, excuse me, it has to operate at 20 amps. So in our case, we can operate down to 1 amp if we see that 1 amp of current for, let's see, about, 8 or 9 seconds. So we have to see a voltage for that long. But anyway, that pretty much guarantees that your breaker's not going to operate and lock out your system. And so if you have a super high current, over 100 amps, it's going to take, less than 1/10 of a second for the disconnector to operate. So now we're going to go on installation coordination. Do we have any questions so far? All right, good stuff.
This time, Patrick.
Okay, sounds good. So there's kind of 3 things that we'll have to kind of pull together, and this can get kind of deep. Go ahead and apologize in advance, but installation coordination is very important, as far as designing your system or just making sure your system is properly protecting your equipment. So I guess before we start, the 3 things are your arrestor discharge voltage, which that's from a catalog or a sales drawing, or from those 2 things. And then so your line leads from your ground and line side add voltage to the discharge voltage as well. So that's important. And then also you can, when you throw in elbow arresters, so underground. I'm not an elbow arrestor specialist, but I know enough to kind of get me in trouble. So those 3 things kind of work together to really provide the most benefit for your system and most protection. So high level, if you don't remember anything else, remember that to avoid excess lead length, so this can raise discharge voltage of your arrestor. So your leads should be flexible so that you do have a visual indication of if the arrestor operates, and so you can install future installations without too much trouble. So like I said, the protective level will be the combination of arrestor discharge voltage from a sales drawing or catalog, in addition to the voltage drop across your line leads. So it gets even more hairy here. Not all leads add to the discharge voltage. Only leads that are in parallel with the protected equipment and it carries surge current. So in this case, you have a line lead from the arrestor here to the cutout. That is included in your lead length, and then your ground, the distance to the common ground. So that would be like to the grounding on the transformer can. So your line from the conductor to the cutout is not in parallel with the protected equipment, so that does not count towards your discharge voltage adder. So pretty much, if you have a question about this, please reach out to me. I do it not every day, but at least once a week. So if you have any questions, feel free to reach out to us. We'll be glad to help you. Like I always say, a few minutes on the phone with us can really help and save you a lot of time and money down the road with any questions regarding installation coordination and TOV. So we're kind of going to talk about a transformer mount application for a second. So here's a good example because there's virtually no, well, very little lead length here. So you have your transformer ground strap here, which is, I think they're 12 to 18 inches, so not much. And then we have our little flipper fuse here. And that, once again, that's super short and direct. And we have a nice direct path to the conductor. So it's not putting a mechanical strain on the arrestor, but it's not wasting any length either. So this is a very good example of, how to get the most out of your arrestor, the most protection out of your arrestor. So now we're going to talk a little bit about riser poles. So this is where you really can get into trouble with installation coordination. So for a second, let's just look and say we do not have an elbow arrestor in this. This is a pad mount transformer, like on the little green boxes. So we don't have an arrestor here, and this is an open circuit. So it's not, a breaker's open in here somewhere. So we have a surge current of unknown magnitude travels down towards the riser. The arrestor shunts it to ground and, takes most of the voltage away and has a discharge voltage of 35 kV. So that 35 kV is going to go, down the riser and into this box. And it's going to hit that open circuit and come back and double. So you're going to have 70 kV coming back up the line to the arrestor again, super quick. So that's why we offer the riser arrestor, because it has a larger MOV block and it can handle that, second surge of that double voltage. So it's super important. That's why, all big manufacturers offer a riser application or a riser arrestor. So like I said, three things are the line lead length impact, and an elbow arrestor, and then the class lead arrestor here. So ideally a riser pole arrestor, because discharge voltage is lower and it can handle the second voltage doubling effect. And we'll go over a few more examples here. So this is kind of the IEEE 6222 standard, kind of summarizes this. So we need to compare the doubled sum of discharge voltage. So in this case that we just talked about, it's 35 kV doubled to 70. And you need to assume discharge current and the connecting lead voltage with transformer and cable BIL. And it's recommended to have a protective margin of at least 20%. That's what IEEE recommends. And so for this case, dry insulation means cable insulation. So with no elbow arrestor, the maximum voltage stress will be 2 times the front of wave. And I haven't talked about that much, but a front of wave is just a wave shape that is possible to occur from nature. So that's generally from a lightning strike, and it's just a super fast rising wave. So that's why you have such a voltage adder. And that's listed here, wrong way. So this would be your 0.5 microsecond rise time, or your steep front wave. That means your front of wave. So this is going to be the worst case scenario as far as discharge voltage for your arrestor, especially with regards to line lead length. So as you can see, well, I'll go back for a second. This is our heavy duty arrestor, our PDV100 discharge voltage. So there's not a whole lot of difference in between the heavy duty and the riser pole, as you can see here, at lower voltages, at 3, 6, 9, up to about 12. But after you get to 12, this is where the riser pole really tends to kind of shine a little bit and has a good bit lower discharge voltage. And that makes a big difference when you double it. So that's another, thing to consider. So this is another excerpt from the 6211 standard about when you include underground arrestors. So pretty much same thing here. A conservative number to use for coordination is the discharge voltage of the riser pole arrestor plus 1/2 of the 1.5 Ka discharge voltage of the reflection point arrestor. So that would be an elbow arrestor in the green box. So this is kind of a good rule of thumb. It just says here values will change, depending on manufacturer, of course, but this is a very, very close estimate that you can use if you don't have a manufacturing or a sales drawing in hand. So this will all make a little more sense in a second. Bear with me. So here's your discharge voltages for your elbow arrestor. And once again, it does not include lead length impact. So it's kind of a lot to keep track of when you're doing this, but it's super important. You know, you can have an arrestor in system and it ends up not protecting your equipment because you have too much lead length, which would kind of stink. So here we have a lot going on. And this is just your calculations that were mentioned in the past couple slides. But the most important thing to look at here is your protective margin. So over here for an 8.4 kV MCOV arrestor, this is without an elbow arrestor. This is comparing your PV100 Optima to your PVR Optima. So in this case, both of them are fine with a BIL of 95 kV. You know, no problems here. You're well over your the 20% recommended, so nothing to worry about. So here, this is with an elbow arrestor. So you can see how your protective margin benefits from having an elbow arrestor. And we'll kind of go over the next few examples really quick, just to kind of see where it starts to really jump. Your protective margins are hurt at higher voltages. So this is at 8.4 kV. The next one is at 15.3. So this is without your elbow arrestor. You're at 3% and 17%, even with the PVR Optima. So you're not really in a good spot here. And so simply adding an elbow arrestor in that pad mount box, your margins are healthy again. You know, everything's protected and it should be fine with the IEEE guidance. So 15.3 will move up again to a 22 kV. So this is where you really have to be careful. You're terrible on margins with no elbow arrestor. Even with the PVR Optima, it's not going to work. You know, if with a front of wave surge event happening, your equipment is very likely to be damaged. And so even with a PDV100 with an elbow arrestor, you're still kind of in the red. So this is where, you know, running through an installation coordination study with us, we can really make sure you are where you're supposed to be. So here we have the elbow arrestor and an appropriately sized PVR Optima, and you are in the clear at this 22 kV. So I know that was a lot, but if you have any questions, please stop me or reach out. Shoot me an email afterwards, whatever. That's pretty much going to wrap it up. I hope it didn't leave you too bad at the end. These are the resources that we kind of use to put these together, and these are great reads. If you have questions or I didn't explain something good enough, the application guide is great, and NEMAarresters.org is a great resource to just kind of, if you have any kind of arrestor questions or just want any sort of training. So we'll open things up for questions now if you guys are ready.
All right, thanks, Patrick. Just a reminder to our attendees, if you have any questions, please use the chat function and direct those towards AIEC, and we'll moderate them for you guys. The first question we do have, though, Patrick, is what field testing does Hubbell Power Systems recommend for distribution arresters?
Sure. So we don't require field testing, first off. We routine test all of our arresters before they leave the factory. So field testing is definitely not required. And that goes for pretty much anyone. You know, any reputable manufacturer should be designed to immune degradation, excuse me. So most field testing is not required or even recommended. If you feel like you have to do it, our infrared analysis is the most recommended. It's best to take a shot of several arresters on the same system at the same voltage and compare the difference. It's kind of hard to nail down a specific, you know, if it's 10 degrees warm, that means you need to throw it away. You know, it's better to compare it over time and just see how it's trending, but we definitely don't require it.
All right, the next question that we have is why is the system grounding type important to consider when selecting the MCOV rating?
Okay, well, the type of grounding essentially just determines the amount of neutral shift during a fault on a system. So the resulting TOV on the arrestor could cause damage unless it's sized for that TOV. This is something that we can definitely run through and help you select a proper size with your system information.
All right, the last question that we have is, how does MCOV differ from the duty cycle rating?
Yeah, we get this one a good bit, actually. Duty cycle rating is a legacy term, and it honestly holds no value with selecting an arrestor. So that's just something that's kind of been held on for over the years. That was more applicable during our silicon carbide gapped arresters. So back in like the 60s and 70s. So the duty cycle was the power frequency voltage that the arrestor could pass on a duty cycle test per the IEEE standard. And that was, the duty cycle was actually completely removed during the 2020 edition of the IEEE 6211.
Well, Patrick, that's all the questions we have for today. I would just remind our participants today, if you have additional questions after this, it looks like Patrick's got his contact information up there. I'd say feel free to reach out to Patrick. He'd be happy to answer any questions you might have. Patrick, great job today. We appreciate your time, and I thank you for your presentation. It was very informative.
Absolutely. Thank you guys for having me up. I'm glad to meet all of you.
All right, coming up after lunch at 1 o'clock, we have utility underground and above ground enclosures. This one, our previous one, and the one after lunch all qualify for PDH credits. So if you're an engineer looking to continue your credits, this is a good way to do that. Also, just a quick reminder for those of you that maybe missed some of our past presentations, those are all still available. If you go out to aiec.coop/webinar weeks and click on the archive link, you'll have access to all of our previous webinars. And with that, that concludes our webinar series for this morning. We'll come back after lunch. See you all at 1 o'clock. Thank you very much.
Thanks, Patrick.
Yep. Thanks, guys. Have a good one.